welcome.
Alright, let's start. Hello everyone, welcome to the Way Forward meetup. My name is Paweł Góra and today I will give you an introduction to quantum computing. So as you can see, the Way Forward community provides a platform for software professionals to discover and explore new trends in the technology field. Learn from one another, get inspired and have fun with fellow professionals. So I hope that today you will learn a lot about quantum computing, and I hope that I will inspire you and you will have fun as well. So as you can see, I have several affiliations. So my background is in math and computer science, and I'm affiliated at the University of Warsaw. But at the same time, I'm also a board member of QWORD, which is an international initiative aiming to support education and building open global ecosystem in quantum technologies. I'm also the coordinator of its local QCousin here in Poland that is called QPoland. And I'm also founder and CEO of the Quantum AI Foundation, having similar goal, aiming to support education, research and collaboration in new technologies, especially quantum computing. So today I will tell you about quantum computing. So what exactly the quantum computing is? The simple answer is that these are computations according to the laws of quantum mechanics. And the longer answer, well, this will be the whole lecture, in fact. So what exactly is quantum computing and quantum mechanics, right? So even in this simple answer, we have the word quantum. So what does the word quantum actually mean? So in physics, a quantum is the minimum amount of any physical entity involved in an interaction. And the fundamental notion that a physical property can be quantized is referred to as the hypothesis of quantization. And this means that the magnitude of the physical property, like energy, can take on only discrete values consisting of integer multiples of one quantum. Sounds interesting, isn't it? So why we should bother? Why it's not only interesting but also important? So the reason is that our world is inherently quantum. And when we talk about computing and algorithms, then of course we can analyze computational complexity like time complexity and space complexity of algorithms. We can prove the correctness of algorithms, but we should also remember that at the end of the day we would like to implement our algorithms and run them on physical devices. So, and these physical devices are governed by the rules of the physical world, which is inherently quantum. We know it from more than 100 years, from more or less the beginning of 20th century. And so this is the date of formulating the famous Max Planck's postulate, which is considered to be a milestone of the beginning of the quantum mechanics. And this postulate basically says that the electromagnetic energy could be emitted only in quantized form. By quantized form, we mean that this energy is proportional to the frequency of a photon or electromagnetic wave, and there is something like the Planck's constant involved, and there is an integer number. So it cannot be an arbitrary value of energy, right? So it can be only integer multiplies of some value, right? And so we have this quanta of energy here, and it may have interesting consequences. For example, maybe some of you also heard that there is a famous Landauer principle, which says that there is a minimum possible amount of energy required to any logically irreversible manipulation of information, like erasing one bit of information. And in this case, this minimum amount of energy is proportional to the temperature of the environment, and we also have something that is called the Boltzmann's constant. So we can say that we cannot run our computations totally for free. So there are some bottom limits, some lower limits for the energy that is required for running some computations. So this is just one of the consequences of the laws of physics. But of course there might be some other interesting consequences. And as you probably know, at the beginning of the IT industry or computer science in general, computer elements were very, very large. The computers occupied large spaces, like very large rooms, and they were much, much bigger than the computers that we have nowadays. But people like famous physicist Richard Feynman started thinking whether the computer elements can be smaller, right? And even the Feynman said that there's nothing that I can see in the physical laws that says the computer elements cannot be made enormously smaller than they are now. And in fact, there may be certain advantages. In fact, people realized that computer elements are becoming smaller and smaller with time. Gordon Moore, one of the employees in Intel, realized that the number of transistors in a dense integrated circuit doubles about every 2 years. So at the beginning it was more or less once per 1.5 year. And this prediction proved accurate for several decades and has been used in the semiconductor industry to guide long-term planning and to set targets for research and development. But the Moore himself in 2015 said that I see Moore's law dying here in the next decade or so, and even the Intel, the company producing processors, realized that the pace of advancement has slowed. So now this doubling of the density of transistors is not once per 2 years, but once per 2.5 years. So this is the technological limit, but in fact, when we also consider the costs, then we can observe that in contemporary computers that are sold, the space of advancement is even smaller. But Intel said that this trend will continue thanks to something that is called hyperscaling. But now the question is, can this trend continue forever? So if it has to continue forever, then about 2035, 2040, the size of a single transistor should be more or less of the size of a single atom. And probably much earlier we'll have serious difficulties with building transistors and building computers. And in fact, even nowadays, or even about 10-15 years ago, there were already some serious difficulties in just building smaller and smaller transistors and integrated circuits. So what we can do and why there are such difficulties? So the reason is that in such a small scale, like a single atom, we have a bit different forces and that are just governed by our laws of physics that may have impact on our technology, on the transistors, for example. So can we build the hardware in a bit different way in such a small scale, and can we run computations in a bit different way? And there are such ideas, this idea in fact originated about 40 years ago. Again, Richard Feynman, who is considered as one of the fathers of quantum computing, but as far as I know, he was not the first person who started thinking about it. Imagine that we can make a computing device in which the numbers are represented by a row of atoms, with each atom in either of the two states. That's our input. And then the Hamiltonian starts Hamiltonianizing the wave function according to the Schrödinger's equation. The ones move around, the zeros move around, and finally, along a particular bunch of atoms, ones and zeros occur that represent the answer. Nothing could be made smaller, nothing could be more elegant, no losses, no uncertainties, no averaging. But that's the question, can we do it? So since we are talking about quantum computing today, then you probably know that we can already build some quantum computers. They are still small, they are still noisy, but they already exist. So here is just an example, right? So this is Bristlecone, one of the Google's quantum processors to the left, and on the right is a cartoon of this processor. Each X represents a qubit with nearest neighbor connectivity. So here we have the word qubit used for the first time. So it's time to explain the difference between classical computers and the quantum computers. So in case of classical computers, as you probably know, we have classical gates like AND or NOT, and we have bits, right? So bits may be in one of two states, 0 or 1, and they can be an input to the classical gate, and the classical gate just produces the output, which can be again 0 or 1. So it's relatively simple. But in case of quantum computers, we have qubits and quantum gates. So what's the difference? So I said that in case of a bit, the state may have a value 0 or 1. So mathematically it's something very simple. It's an element from the set 0, 1. But in case of quantum computers, a state of a qubit may be a superposition of states 0 and 1. So the qubit may contain some information about the state 0 and some information about the state 1. Mathematically, it's something much more complicated because it's a unitary vector of the two-dimensional Hilbert space over complex numbers. Sounds difficult, right? But I will try to give you an intuition, at least how to think about the states of qubits. So another difference between classical computers and quantum computers is that in case of classical computers, each state is determined. So we can know exactly whether the state is 0 or 1. We can change the state from 0 to 1 and vice versa. But in case of quantum computers, to get values 0 or 1, we have to do a measurement which breaks this superposition. So it turns out that the probability of getting 0 or 1 after the measurement depends on the state of the qubit, so depends on this unitary vector of the two-dimensional Hilbert space over complex numbers, and our quantum gates can just modify the states of qubits and then modify the probability of getting 0 or 1 after the measurement. So this is the representation of a state of a qubit, of the quantum superposition. So we have something like 0 and 1 in some strange brackets. So this is the so-called the cat or bracket notation, or Dirac notation. So these 0 and 1 are our basis states. So they are orthonormal base of a quantum system. So we can, instead of thinking about 0 and 1 as numbers, we should think about them as just vectors. But also not arbitrary vectors. It should be an orthonormal base of this two-dimensional Hilbert space. So we can think about them as vectors 1, 0 and 0, 1. And A and B here are complex numbers, such that their squares of their amplitudes are probabilities of getting 0 or 1 in a measurement, so that the sum of squares should be equal to 1. I'm not sure how familiar you are with complex numbers, but maybe just to recall, each quantum number has two components. So in fact we can also think about a complex number as a point in two-dimensional space of real numbers. But beside two coordinates, the real coordinates and imaginary coordinate, we can also represent the complex numbers using some other two numbers, using an angle and using the amplitude. And it turns out that if we have two complex numbers representing these numbers a and b, so this coefficient before 0 and 1, our orthonormal base, then only the relative phase, so the difference between phases, difference between these angles, has any physical significance, right? Because the phase of the quantum system is not directly measurable, so we can only measure this difference. And the consequence is that multiplying these complex numbers by a unitary vector does not change the quantum state. So this is the simple arithmetical exercise, so arithmetics of complex numbers. There exists a complex number such that we can just multiply both complex numbers by this complex number with the amplitude 1 in such a way that we'll have the real number, not complex number but just a real number before 0 and another complex number before 1. And since we have the real number, which still should have an amplitude lower than 1, it means that this is just a cosinus of some angle, right? And if we know it, then we can just determine the value of the second coefficient staying just before this vector 1 by just having or using another angle. So we need two angles to determine the state of a qubit. And it means that we can transform this representation to spherical coordinates, which means that our states of qubits can be also represented as points on a sphere that is called the Bloch sphere. Yes, so here is just a figure presenting this Bloch sphere, and in case of classical computers, the state of a bit can be 0 or 1, so these are just these antipodic points, right? So we have 0 at the top and 1 at the bottom. But the state of a qubit can be any point on the Bloch sphere, and sometimes we also say that quantum computing or computations using just a single qubit is just a journey on a Bloch sphere, because it turns out that our quantum gates, in case of operating on just a single qubit, just correspond to rotations of the sphere, as we'll see. So in this case we have rotations, right? So the rotations are our quantum gates. So in case of classical gates, as you remember, we can just change 0 to 1 and 1 to 0, but in case of quantum gates and quantum states, we can just rotate our sphere, and some points may just be transformed to another points. Alright, so these are just some notable examples of quantum gates. There is a very important Hadamard's gate, which transforms the quantum state 0 into superposition of states 0 and 1, such that there's the same probability of getting 0 or 1 after the measurement. There are gates that are called Pauli gates, so there is Pauli X gate, Pauli Y gate, and Pauli Z gate. As we'll see, they correspond to rotations by 180 degrees around one of the axes in this Bloch sphere, so around X, Y, or Z axis. We can also parameterize our rotations using another angle, so it doesn't have to be 180 degrees. And we may also have quantum gates operating on more than one qubit. So for example, the most important gate operating on more than one qubit is CNOT gate. So it operates on 2 qubits, and 1 qubit is just a controller for the negation, so for this X Pauli gate on the second qubit. So I said that this gate, the CNOT gate, is important because any quantum circuit can be simulated to an arbitrary degree of accuracy using a combination of the CNOT gate and single qubit rotations. Alright, so here let's talk about these quantum gates in details. So here we have this Hadamard's gate. So when we define a quantum gate, it is sufficient to define how this orthonormal, the vectors from this orthonormal base, so our 0 and 1, are transformed, right? Because each vector, so each possible state of a qubit, each superposition of this state 0 and 1, is just a linear combination of vectors 0 and 1, and it means that all the quantum gates are also linear operations in this case. So we also have unitary matrices corresponding to these quantum gates. So this is just due to the fact that all quantum if we have quantum states, then the sum of probabilities of just getting specific states should be equal to 1, right? And it turns out that in case of this Hadamard's gate, this gate can be also represented as a rotation about the axis x plus z, or alternatively, first we can rotate by 90 degrees around y-axis and then by 180 degrees around the z-axis, right? But we can also define this gate using a matrix that is called the Hadamard matrix, right? So and then, as we know that 0, our vector or state 0 corresponds to the state 1 0, or to the vector 1 0, right? And the state 1 corresponds to the vector 0 1. Then if we know how to multiply matrices by vectors, then we can get a new vector, and then we know what's the new representation of our new quantum state in our orthonormal basis, in this linear space, in this Hilbert space, in fact. So that's why for each such quantum gate we may have matrix representation. We may also have a definition of transformations, or we can just define how exactly our orthonormal vectors, orthonormal base is transformed to which vectors. And in case of single qubit gates, we can also represent these gates by rotations of this Bloch sphere. And each quantum gate has also a graphical representation. So in this case, this is just a letter H. All right, let's go further. So here is the X Pauli gate, and it just corresponds to negation, because the state or vector 0 is just transformed to the state 1 and state 1 to state 0. So this Pauli X matrix corresponding or defining this quantum gate is relatively simple. This is equivalent to of the NOT gate from classical computing, let's say. And it can be also represented as a rotation of 180 degrees about the axis x. This is the generalization. So in this case, it's a rotation around the y-axis, and it's parametrized rotation, right? So it can be this rotation through another angle in radians. All right, and this is the CNOT gate. In case of CNOT gate, so as I said, CNOT acts on 2 qubits and performs the NOT operation. So here's the NOT operation on the second qubit only when the first qubit is 1, and otherwise it leaves it unchanged. So here is the matrix. So in this case, the dimension of this matrix is 4. So in general, when we have quantum gates operating on n qubits, then the corresponding matrix should be 2 to the power of n dimensional. Alright, and in fact, the true advantage of quantum computing comes when we have many qubits, right? So, for example, so here's just an example. We can just prepare n qubits, which are initially in the state 0, but then we apply Hadamard's gate. So then, after application of the Hadamard's gate, for each qubit we have the probability of getting 0 or 1 in the measurement, and that is the same, right? So it's just equal to 1 over 2. Then we can represent all possible 2 to the power of n bit numbers using just n qubits, right? And then we can apply some quantum gates to 1 qubit or to many qubits. Then we may have a quite large quantum circuit operating on many qubits. And thanks to this quantum circuit, we can just modify the probabilities of getting 0 or 1 after the measurement for each qubit independently. So at the same time, we can operate on all 2 to the power of n bit numbers. So, but we just modify the probability of getting one of these numbers after the measurement. And here's an example of a quantum circuit with 8 qubits. So we have 8 quantum registers to the left, and at the bottom we have 8 classical registers on which we can store the results of our computations, and we can pass these results further. And in case of 3 qubits, in case of qubits number 3, 5, and 7, we don't have any quantum gate, so we just perform measurement. When all the states were initially in the state 0, then with probability 1 we just get the result 0. So that's the result of the measurement for qubits 3, 5 and 7. In case of qubit 6 we have this ex Pauli NOT gate, which means that with probability 1 we'll get the value 1 after the measurement. But interesting things happen for qubits 0, 1, 2 and 4. Because in case of the qubit 4, we first apply the Hadamard's gate, which means that when we do the measurement of the qubit 4, then with the probability 1/2 we'll get 0, and with the same probability we'll get 1. But then this qubit is just entangled with qubits 0, 1, 2 using the CNOT gate, which means that the qubit 4 is controller for negation for qubit 0, 1 and 2. So if the state of this qubit 4 is 0, then the state of qubits 0, 1, 2 will be 0 as well. But then we apply the NOT gate to qubit 0, so it becomes 1. So if we get the value 1 after the measurement with probability 0.5, then we will always get the results 0 for qubit 0, 1 and 2. And if we get the result 0 for qubit 4, it means that before applying the NOT gate it was 1, and it means that this CNOT gate is triggered, so the NOT operation is applied to qubit 0, 1, 2, and the result of measurement for qubit 0, 1, 2 will be 1. So in fact there are two possible results when we consider all 8 qubits together, all 8 quantum registers and 8 classical registers. So we can get either, so just reading from the bottom and from 7, 0, 1, 0, 1, 0, 0, 0 or 0, 1, 0, 0, 0, 1, 1, 1. And these are just representations in the ASCII code of the first letters of my first name and last name. So I can say that I've just, in this quantum circuit, I've just encoded my initials. Alright, and you can do the same exercise if you want. So this was prepared using IBM Quantum Experience, which is publicly available for everyone. So this is just an example showing that using n qubits we can potentially process all 2 to the power of n bit numbers at the same time. So in this case we had only 2 8-bit numbers processed at the same time using n qubits. But in case of classical computers, when we have 8 bits, then we can store only 1 n-bit number at the same time. So here we can see that there might be some advantage and maybe even exponential advantage of quantum computers. There is also at least one more potential advantage of quantum computers. In case of classical computers, the results are deterministic. So we may have randomness, but in fact it's a pseudo-randomness. So we have some generators of random numbers. And in case of quantum computers, we may have real randomness. By mean, I mean the randomness that we can expect in the quantum mechanics. And thanks to this, we can easily sample from probability distributions, which might be difficult for classical computers. So there's an example is the Boltzmann's distribution, which also has applications in machine learning, for example. So sampling from difficult distributions is just one example of possible applications of quantum computing. Quantum cryptography on breaking some classical cryptography algorithms is another example, so I will talk about it soon. Solving combinatorial optimization problems, very important application of quantum computing, because combinatorial optimization problems appears almost everywhere in machine learning, AI, finance, transport, logistics. So almost everything is optimization. And since we do computations on computers with limited finite memory, then in fact we can say that almost everything is, or everything we do on classical computers is combinatorial optimization, or can be considered as combinatorial optimization. We can also simulate quantum processors, which may find applications in discovering new materials or new drugs. Alright, so let's talk about breaking these cryptographic codes. So in current cryptographic algorithms like RSA, for example, we often assume that some computational problems are difficult for classical computers, right? So, for example, the difficulty of RSA is based on the difficulty of the factorization problem. So, as you know, it's relatively easy to multiply two n-digit numbers. So we can do it in the time, pessimistic time, asymptotic time, n log n. But when we want to factorize n-digit number, it turns out that it's more difficult because no algorithm has been published that can factor all integers in polynomial time. But the interesting thing is that neither the existence nor non-existence of such algorithms has been proved. It's generally suspected that they do not exist, and hence that the problem is not in class of problems that can be solved in polynomial time, but it hasn't been proven yet. And we use this cryptographic algorithm even without such a proof. The best published asymptotic time algorithm is called the general number field sieve. So you can see the time complexity of this algorithm, and you can see that this is an exponential complexity. But when you have quantum computers, we know how to do it in polynomial time. In the 90s, a famous Shor's algorithm was discovered and published. So this is the time complexity of this algorithm. So as you can see, it's polynomial time, even considering the fact that we have to repeat computations many times, about log n times. So this log or log n is already included here in the complexity, in the analysis of time complexity, but it's still polynomial time algorithm. And the magic happens here. So this is so in fact this is a hybrid algorithm in which we have the classical part, but there is also a quantum subroutine which is responsible for finding a period of a long sequence using the inverse quantum Fourier transform. So this is this inverse quantum Fourier transform. So this is where the magic happens. Alright, another application, solving combinatorial optimization problems. So in combinatorial optimization problems, we search for the best of many possible combinations, and this includes problems like scheduling challenges, such as should I ship this package on this track or the next one, or what's the most efficient route a traveling salesperson should take to visit different cities, right? So the traveling salesman problem is an example of combinatorial optimization problems. And the interesting and important fact is that physics can help solve these problems because we can frame them as energy minimization problems. And a fundamental rule of physics is that everything tends to seek a minimum energy state. So, for example, objects slide down hills, hot things cool down over time. And this behavior is also true in the world of quantum physics. And there are ideas to just employ this phenomenon in quantum computing. And there is an area of quantum computing that is called adiabatic quantum computing. So in order to explain it, it's good to first explain what exactly the word adiabatic means. So an adiabatic process is a process that does not involve the transfer of heat or matter into or out of a thermodynamic system. So in such a process, the energy is transferred to the surroundings only as work. And there is something that is called the adiabatic theorem, which basically says that when we prepare our quantum system in such a way that it's at the beginning it's in a ground state, so in a state with the minimum energy, and then we evolve this quantum system in the adiabatic way, so according to the rules of the adiabatic process, then the system remains in the ground state, so in the state of the minimum energy. And how we can use it. So first, a potentially complicated Hamiltonian should be prepared such that its state describes the solution to our optimization problem. So here we have the word Hamiltonian. So in general, for the purpose of this lecture, you can think about the Hamiltonian as a function that takes the state of a given quantum system and returns the energy of this quantum system in a given state. So it's the function. So we have a function, we have a quantum system for which this function describes the energy depending on the state of this quantum system.
And next we should also prepare a simple Hamiltonian. For example, we can use this Hadamard gates to just produce superposition of all possible states, and then we can easily initialize this quantum system to the ground state, so to the state with the minimum energy. So in case of applying this Hadamard gate, this is relatively simple. And then we can evolve our quantum system, for example, by modifying the strength of the magnetic field. And if we do it in an adiabatic way, and if we do it slow enough, then in theory, at the end, we should end up in the global minimum of the final Hamiltonian. And now, if we design our quantum system in such a way that the final Hamiltonian, so this final function, corresponds to our optimization problem, so to the function that we want to optimize, then potentially we can solve optimization problems using quantum computers, and maybe we can do it very fast. But there are some issues here. First, before I talk about the issues, first I will maybe explain why it can work and how it can work. So the reason is that there is a correspondence between mathematical problems that are called QBO, so quadratic unconstrained binary optimization, so I will soon tell about it, and something that is called the Ising model. So the Ising model is a model of ferromagnetism that is traditionally used in statistical mechanics. And here we have some binary variables that correspond to spin up or spin downs, or values +1 or -1, if we just want to describe the energy of the system. And we have some relationships between the spins, so they might be couplings or correlations or anti-correlations, right? And then the objective functions of the Hamiltonians of this function expressing the energy of this ferromagnetic can be expressed using this Ising model, right? So we have the values of spins +1 or -1. We have some parameters, but this is just a function of many binary variables, and maybe this is the function that we could optimize somehow, right? So according to this adiabatic theorem, if we first prepare a quantum system that will be in the state of this global minimum, and then apply or change the strength of a magnetic field, then at the end we should achieve a system in which the energy, or that will be still in the state of the global minimum, let's say. So that's the theory. And now is this correspondence, right? So I just said that in computer science or mathematics we have something that's called QBO, quadratic unconstrained binary optimization. So as you can see, this is a similar family of problems. So we have a function of many binary variables, but this time corresponding to zeros and ones. But again, we have some parameters, right? So if we can define our optimization problem as such a QBO, then we can just encode it, translate it in a ferromagnetic, and maybe we can find the global optimum of such a function thanks to this adiabatic process. So that's the idea behind quantum or adiabatic quantum computers. Here there's already the name quantum annealing, because in practice there are some issues with this approach. So the first issue is that, so first of all, it's difficult or almost impossible. Maybe some physicists may even say that it's impossible, or we don't know how to do it now, to just ensure that the process will be 100% adiabatic, so that there is no transfer of heat or matter into or out of this system. So it's at least it's difficult, maybe it's even impossible. And so that's the one thing. Another thing is that according to this adiabatic theorem, in order to stay in this state of this global minimum for the whole time, we should do this evolution slow enough, and the pace of this evolution also depends on this optimization problem that we have to solve. So it is expected that using this approach, unfortunately, we'll not be able to solve NP-hard problems exactly in a reasonable time, like polynomial time, but there are chances that maybe we'll be able to just build some better heuristics, meta-heuristics, solving these optimization problems by finding approximate solutions. maybe 5% worse, but if we can find it very fast, then sometimes it's much better to find solution that is good enough and can be found in just milliseconds than to wait many hours or many days for a solution that will be really optimal. Okay, so we can do such a magic thanks to another physical phenomenon that is called quantum tunneling, right? So then we can ensure that, so by modifying the strength of the magnetic field, we modify also this Hamiltonian, and we modify the function. And when we modify the function, it may turn out that in some point we are in a point that is a global minimum, but after we modify the function, this point is not the global minimum anymore. But thanks to this quantum tunneling, it can jump to another point that is the global minimum. So such magic may happen in a case of quantum mechanics. So what might be the applications of this approach? So there are some applications, for example, in transportation. So it's not science fiction anymore, because we can already run such experiments, at least since 2017. But so this is just an example on how we can optimize routes of fleets of taxis in Beijing. So this experiment was carried out by researchers from Volkswagen and from a company from Canada. The company is called TWF Systems, and indeed they are probably the only company working on so-called quantum annealers, right? So performing these quantum annealing procedures. So this is a relatively simple example, so that's why I just want to explain it briefly. If you are interested in details, here's the link to the paper that is titled Traffic Flow Optimization Using Quantum Annealer. So what did they do? So first they built a road network, and they had routes from real GPS data. So it was so this data set was called T-Drive, and was built based on data from taxis operating in Beijing. So these taxis traveled from the city center in Beijing to the airport. And for each car, for each taxi, they added two possible alternative routes between the source, between the city center and the destination. And of course, it was assumed that the cars may share road segments. It was also assumed that the travel time is proportional to the function, that is a square, of a number of cars on a given route. So it's a simplification. So in the real world, it's not exactly the square function, but it's close enough, let's say, right? So it's a reasonable simplification. And now the goal is to minimize the total travel time. So how we can do it? First, we should define these binary variables that will correspond to our spins in a ferromagnetic, right? So in this case, the binary variables qij may be equal to 0 or 1. So being equal to 1 means that the car I takes route j. So as you remember, for each car we have 3 possible routes. So since for each car we have 3 possible routes, then for each car we just want to select only one route, exactly one route, right? So this constraint should be satisfied for each car. So for each I, when we just sum all variables, then this sum should be just equal to 1, right? So when we just subtract 1, then it should be equal to 0. Then we define the set of those variables that are associated with routes that share a given street segment S. And for this street segment, according to our assumption, we define the cost of traveling on this street segment for all cars. So that's the total cost for all cars. This is proportional to the sum of cars traveling through this road segment, so to the number of ones assigned to our binary variables, right? And we have the square because that was our assumption. And then in order to get the total cost, we have to just add all the cost for all segments. And so what may happen if we stop here, right? So then we can run the optimizer, we may run our quantum annealer, and the answer will be 0, 0, 0, 0, right? So the 0 assignment. We can just assign 0 to all binary variables, and that's the minimum of this function, right? But it's not a good solution because this constraint is not satisfied. So in order to satisfy this constraint for each vehicle, we have to add this component and to set the value of a parameter lambda to be large enough in such a way that when we run the solver once again, then we ensure that this component is equal to 0, because otherwise it cannot be lower than 0, it can be potentially greater than 0. But the value of the parameter lambda should be large enough that when this component is greater than 0, then the value of the whole function will be so large that this solution cannot be found by a reasonable solver. So that's why we ensure that in any solution found by our solver, by our quantum annealing algorithm, this constraint will be satisfied. There are also some modifications. So for example, we may just say that this value of this parameter will be lower, and with some probability this constraint will be satisfied, but with some probability it will not be satisfied. But maybe if it's satisfied with a low probability, maybe this the value of the cost will be lower, so it can be still a good solution. Why not? But anyway, the important thing is that this is a QUBO formulation, because all these binary variables in a quadratic form, right? So we can encode this problem, this optimization problem, on our quantum annealer. And the researchers from D-Wave did it. They ran experiments with 418 cars, so in total there were more than 1,200 logical variables. So the space of the possible solutions is astronomical, as you can see, but after just about 22 seconds of computations, this quantum annealer was able to find the assignment of roots that was reasonable, let's say, right? So better than the solution that happened in the real world. So the researchers didn't analyze whether this algorithm may be better or not than classical algorithms. I'm pretty sure that many classical algorithms like genetic algorithms or memetic algorithms, CMAES, maybe even simulated annealing, will be able to find similarly good solutions in a similar time, or maybe better solutions. There was no such analysis in this paper, but anyway, this is an interesting example showing that we can already solve some important real-world problems using quantum computers. So it doesn't mean that we can solve these problems faster and or better than on classical computers, because our classical computers are also already very powerful, right? We started working on classical computers about 80 years ago. But in case of quantum computers, as you have seen, we started about 40 years ago. So classical computers are very powerful, and it may be difficult to just get any advantage, but it may happen. And in fact, some advantages, some quantum supremacy cases have been already proposed. So this may find applications in improving logistics, like solving traveling salesman problem, and similar optimization problems in logistics, like the vehicle routing problem, pickup and delivery problem, van pooling services. And I'm personally collaborating with several logistic companies interested in such solutions. I've also already published several papers, research articles on this topic. There might be applications in quantum machine learning, because if you are interested in quantum machine learning and have some experience with quantum machine learning, then you probably know that machine learning is almost all about optimization. So even if you train your neural networks, then your goal is to find the set of weights that will minimize the lost function on a given training set, more or less. So at the end, of course, you would like to minimize the error on the test set or validation set, but you train your models on the training set. So this is optimization, and almost everywhere in machine learning we have optimization. And since we do it on classical computers in which we have a finite memory, we can say that this is a combinatorial optimization. But we can also use some other techniques like backpropagation or gradient descent, of course, but we should know that potentially some combinatorial optimization algorithms like genetic algorithms can be applied to many problems as well. And there are many ideas. So I've personally encountered research articles trying to apply quantum computing to almost all important, interesting machine learning techniques. So this is an interesting domain for research, right? So we can think about classical or quantum algorithms, classical or quantum data, and for all these types of quantum machine learning, there are also different approaches on how to tackle problems from this area. These are probably the most popular algorithms for this quantum machine learning, let's say. So they are called variational quantum algorithms like QAOA and VQE. So basically we build a physical circuit that is parametrized, so we can use these parametrized gates corresponding to rotations, and we can just run computations using the quantum computer, get the result, get the expected value, then apply a classical optimizer to find a better set of our parameters, and then try to find even better settings. So that's the basic idea behind this popular variation quantum algorithms. Why it's important? So we are closer to the end. So it's good to know that recently we've observed an interesting progress in this domain. For example, recently IBM announced that they have quantum computer with more than 100 qubits. Xanadu announced that they have quantum computer with about 200 qubits. It's also important to know that there are different approaches to build quantum computers using ion traps, superconducting, or photoning qubits. There is this D-Waves machine that is a quantum annealer. There's idea to build topological quantum computers, right? Let me check the questions. No, we don't have any questions. So let's go on. And beside the advancements in hardware, it's also good to know that there are some advancements in the software as well, because there are already some software development kits with access to quantum computers on which we can, or using which we can just develop programs, quantum computing programs that can be later run on real quantum computers or simulators of quantum computers. So what might be the future? Of course, it's difficult to predict the future. The best way to predict it is to just create it, to just work in this domain and trying to do something meaningful in this area. But there are some obstacles on the road to our real quantum supremacy. So the coherence, it's difficult to isolate qubits from the environment. There is error correction, right? So when we have physical qubits, we may have noise due to the quantum gates or due to the measurements. So we may need many physical qubits in order to get just a single logical qubit. Even from the algorithmic perspective, sometimes it's difficult to prove that quantum algorithms will be better than classical algorithms. So the Shor's algorithm is the example, right? So we know that there is a polynomial time algorithm that is able to break our cryptographic codes, but it hasn't been proven that it cannot be done using classical computer, right? And building some quantum gates is also still challenging. So regarding quantum error correction, in the 90s, there was a proof that quantum error correcting codes exist. And 1 year later, it was proved that these codes could theoretically push error rates close to zero. And as Scott Aronson, one of the scientists working in this domain, said that this was the central discovery in the 90s that convinced people that scalable quantum computing should be possible at all, that it is merely a staggering problem of engineering. So from a scientific perspective, we more or less know that can be done or how to do it, but from the engineering perspective, it's very difficult. So these are just examples, or just a single example of a simple quantum error correction code. So assuming that when we have 3 qubits, then at most 1 qubit may suffer a bit flip, we can just represent the qubit or the state 0 as 3 physical qubit 0, 0, 0, and the same or similarly for this quantum state 1, we can just use 3 physical qubits to just represent one logical state 1. And then if there can be only one flip here among these 3 qubits, then we can, after doing the measurement, we'll know what's the correct value, right? But this is just assuming that at most 1 qubit suffers a bit flip in case of having 3 qubits. Alright, so let's go on. I also said that it's difficult to prove that quantum algorithms will be better than classical algorithms, and here is a very interesting example. A few years ago, Scott Aronson proposed to one of his very talented students, Ewing Tang, to work on something that is called recommendation problem. So for many years, it was believed that this recommendation problem is not solvable in polynomial time. And there was a quantum algorithm able to solve it in polynomial time. And Professor Aronson proposed to the student to just prove that this recommendation problem cannot be solved in polynomial time. That would be also a proof that this is the case in which we may have a quantum advantage, important quantum advantage potentially. But this student worked on this topic for some time, but at the end discovered something opposite. So she was able to just invent a totally new polynomial time algorithm for this recommendation problem based on Am I online again?
Sorry.
Okay. Alright, so it looks like I had some technical issues, so sorry for that. I hope that now you can see my slides and everything is fine. Alright, so I started talking about proving that this recommendation problem can be solved in polynomial time using classical computers, which means that we are not able to prove the quantum advantage in this case, but anyway, it turned out that it's still very good to work on quantum computing and quantum algorithms because anyway, we can prove something interesting and useful even for classical computers. So currently quantum computers are still very noisy, so I said that there might be issues that due to quantum gates or due to the measurements. So our quantum gates are not ideal and the measurements are also not ideal. So that's why there are also ideas on how to just take advantage of the existing noisy intermediate scale quantum computers, and there are even frameworks like CERN developed by Google in order to take advantage of this early stage quantum computers. As you know, Google also proved the famous supremacy. So there was an experiment presented, described in a paper in the article in Nature about quantum supremacy using a programmable superconducting processor, and nowadays we have at least two other experiments that proved that quantum computers may have a supremacy. So these are still some rather artificial examples of quantum supremacy. So we cannot say that quantum computers will be able to just help us in solving some important real-world problems nowadays. But this is sometimes it's compared to the first flight of the Wright brothers more than 100 years ago. So the first flight was relatively short, more than or less than 300 meters. But they proved that it can be done, and about 15 years later we already had commercial flights. So it's possible that so we already have commercially available quantum computers, but it is possible that within maybe 10-15 years we'll already have more powerful quantum computers that will be able to just solve some important problems for us. These are just examples of some frameworks, quantum computing frameworks for writing quantum programs. This is PyQL from Rigetti company, Project Q, open source project developed at ETH in Zurich. D-Wave Sleep platform, so this platform for quantum annealing experiments that can be run on quantum annealer from D-Wave. YAO.jl, this is an interesting library because most of the libraries for quantum computing are just for Python language, but YAO is for Julia, and it's expected that Julia might be very useful for quantum computing applications thanks to its very good parallelization properties and and how it is designed. It's quite a modern programming language. Penelane, another Python library, and that was the first library for quantum machine learning. So it was called TensorFlow of quantum computing before Google released something that is now called TensorFlow Quantum. So this is the TensorFlow for quantum computing. There is also a machine learning toolkit from IBM, so Qiskit. Qiskit is probably the most popular quantum computing framework and library nowadays. And that's all for today, so I hope you enjoy it, and sorry for the technical issues once again, and if you have any questions I will be happy to answer. Okay, I don't see questions now. Maybe they'll be posted here soon. Alright, so it looks there are no questions. So thanks thanks for the attendance, thanks for joining. I hope you enjoyed this lecture. If you have any questions in the future, feel free to reach me out. So here are my email addresses and the websites of the Quantum AI Foundation, my personal website, the University of Warsaw. So feel free to contact me. Thank you.